If you fell into a black hole, from your point of view, nothing special would happen as you crossed the point of no return. No flash, no war, no sudden stop. Yet to the rest of the universe, you would freeze, fade, and redshift into darkness, never quite reaching the edge. Two realities, both correct, separated by gravity so extreme it breaks our usual idea of time and space. To understand what really happens, we need to strip away the movie versions and look at the physics of an object so dense that escape velocity exceeds the speed of light. A black hole is not a cosmic vacuum cleaner. It's a region of space-time where gravity has become geometry gone wild, and falling in is less like being eaten and more like sliding over a waterfall in the fabric of reality itself. A black hole begins with mass squeezed into a small enough volume. For Earth to become a black hole, you'd have to compress it into a sphere less than 2 centimeters across. For the Sun, about 3 kilometers. The boundary around this compressed mass is called the event horizon, the radius where the escape velocity equals the speed of light, defined by the Schwarzschild radius, 2 g/m c squared. Outside this horizon, gravity can be incredibly strong, but in principle, you can still escape with enough energy. Inside, every possible path you could take, even if you fired rockets at full power, leads inevitably inward. Not because a force is pulling you, but because space-time itself is curved so steeply that forward in time and toward the center become the same direction. So what happens when you fall? Imagine starting far away, drifting toward a stellar mass black hole, maybe 10 times the mass of the Sun. At first, it feels like any other orbit. Gravity pulls you in, you accelerate, you see the black hole's surroundings brightening as gas in the accretion disk heats to millions of degrees and emits X-rays. Your clock ticks normally. Your heartbeat is boringly ordinary. But someone watching you from a safe distance would see something very different. As you approach the event horizon, signals you send take longer to climb out of the gravitational well. Your image slows, your motions stretch out in time. Light from you is redshifted to longer and longer wavelengths, sliding from visible to infrared to radio. To them, you never quite cross the horizon. You just fade into darkness, asymptotically frozen on the edge. This isn't an illusion. It's what their clocks genuinely measure. General relativity says time runs differently in different gravitational potentials. Near a black hole, time dilation becomes extreme. If you hovered just outside the event horizon of a supermassive black hole for an hour, billions of years could pass in the distant universe, depending on how close you dared to get. From your own perspective, though, you cross the event horizon in a finite time. No drama at the exact crossing. No local experiment can tell you you are now inside. The laws of physics at that point are, as far as we know, the same. But the global structure of space-time has changed in a way you can't undo. Every future path ends at the singularity, a region where our equations predict density and curvature become infinite. Before you worry about the singularity, your body has a more immediate problem: tidal forces. Gravity decreases with distance, so your feet feel a slightly stronger pull than your head. Near a small black hole, this difference becomes lethal long before you reach the horizon. You're stretched along the direction of fall and squeezed sideways. Astrophysicists with dark humor call this spaghettification. For a 10 solar mass black hole, the tidal forces at the horizon are so intense they would rip you apart, well outside your body's tolerance. You'd be torn into a stream of plasma, then into individual atoms, then into subatomic particles, long before you could report what crossing the horizon feels like. But scale matters. For a supermassive black hole, millions or billions of solar masses, the Schwarzschild radius is huge, and the gradient in gravity at the horizon can be gentle. Fall into the black hole at the center of our galaxy, about 4 million solar masses, and you could cross the event horizon without immediately noticing tidal forces. You might survive for minutes, even hours of subjective time as you plunge inward. The universe outside would appear increasingly distorted, light from behind you lensed into arcs and rings, the entire cosmos seemingly compressed into a bright, shrinking patch above as you accelerate toward the center. Meanwhile, your information is doing something very strange. According to classical general relativity, everything about you, your atoms, your memories, simply falls to the singularity and is destroyed. But quantum mechanics insists information cannot be erased. This clash produces the black hole information paradox. One proposed resolution is black hole complementarity. From the outside, all your information is smeared over the event horizon, encoded in subtle quantum correlations of Hawking radiation. Hawking radiation is a quantum effect predicted in the 1970s. Near the event horizon, quantum fields fluctuate, creating particle-antiparticle pairs. One falls in, one escapes, and to a distant observer, it looks like the black hole is slowly radiating energy and losing mass. A stellar mass black hole would take about 10 years to evaporate, far longer than the current age of the universe. But in principle, over that time, it might leak out all the information it ever swallowed. Some physicists argue that to preserve unitarity, there must be a firewall at the horizon, a searing wall of high-energy quanta that incinerates anything crossing. Others think this violates the equivalence principle, a core part of general relativity, which says free fall should feel locally like weightlessness. At the cutting edge, ideas like holography and ER equal EPR try to reconcile these views, suggesting space-time itself may emerge from quantum entanglement. All of this is theory. What do we actually know from observation? We've seen stars orbiting invisible masses, like the S-stars whipping around Sagittarius A at thousands of kilometers per second, tracing out the gravitational pull of a 4 million solar mass object in a region smaller than our solar system. We've detected gravitational waves from merging black holes, ripples in space-time itself, matching general relativity's predictions to astonishing precision. In 2019, the Event Horizon Telescope gave us the first image of a black hole's shadow, a dark circle surrounded by a glowing ring in the galaxy M87. That shadow's size and shape matched the warped photon orbits predicted by Einstein's equations. We can't watch matter cross the horizon directly, but we can see gas heating and brightening as it spirals in, and we can measure how time and light behave in the intense gravity nearby. So, if you fall in, what really happens? From far away, you freeze and fade on the edge, your last signals stretched into oblivion. From your own point of view, you cross an invisible boundary in finite time, maybe feeling nothing at first, then eventually being torn apart by tidal forces and carried toward a region where our current physics breaks down. Your story ends, but your information, in some deep quantum sense, might not. The biggest open question is what replaces the singularity when we finally have a full theory of quantum gravity. Is there a bounce into another region of space-time? A fuzzball of strings? A holographic surface with no interior at all? Until we can unite general relativity and quantum mechanics, the final chapter of your fall remains unwritten. And that's why black holes are not just cosmic trash compactors, but laboratories for the deepest laws of reality we explore here on Terra Nova.